Hi everybody, let's begin with the first question over this exercise for linear programming. For 1 mark, it says the solution set of this inequation is what? Let's talk about the solution set of this inequation, which is 2x plus y greater than 5. So first of all, what you do, you consider this to be an equation, right? You consider this to be an equation, and this, if you consider to be an equation instead of inequation, you get a straight line in your 2D plane. So what do you get? 2x plus y is equal to 5. This is what you consider. Draw this straight line. When you put x equals 0, y turns out to be 5. So suppose this point is 0, 5. When you put y equals 0, x turns out to be 5 by 2, which is 2 point something. So here is suppose that. Fine. So when you have 5 by 2, you get 2.5. So in here basically, if this is 2.5, you have this point and this point. When you join and extend is what you get, the straight line 2x plus y equal to 5. I am interested in the region represented by 2x plus y strictly greater than 5. I am not interested in the set of points for which 2x plus y is equal to 5. So all these points lying on this straight line are actually satisfying 2x plus y equal to 5. I am not interested in such points. So I draw this line as a dotted line. I draw this line as a dotted line because I am not wanting to collect all those points which are satisfying 2x plus y equal to 5. I am interested in the set of points which satisfy 2x plus y is greater than 5. So what do? Pick up any point which is not lying on this line, origin. Put x equals 0, y equals 0, you get 0 plus 0. 0 plus 0. 2 into 0 is 0 plus 0. 0 plus 0 is greater than 5. This is false, and therefore the region not containing the origin is going to be the region represented by 2x plus y greater than 5. This side will not be my region. Points on the line will not be in the set. Only the points on this side of the line is going to be the set of all those points x comma y which are satisfying 2x plus y strictly greater than 5. So this is the region represented by 2x plus y greater than 5. Okay, this is the region represented by 2x plus y greater than 5, and so the region is half plane that contains the origin, no. Open half plane not containing the origin, yes. This is my answer. This is an open half plane which is not containing my origin. Moving to the next question, we have objective function of an LPP is what? So you all know objective function of an LPP is not a constraint, it is actually a function to be optimized, either maximized or minimized. It is a function to be optimized, linear function to be optimized. It is, yes, a relation of the variable, but a more apt option is that it is a function to be optimized. Moving to the next, we have, which of the following is not a convex set? Now see, in here you should always know what these regions are going to turn out to be. Then it becomes very easy for you to conclude about them representing a convex set. First is 2x plus 5y strictly less than 7. We just now dealt with such a case. 2x plus 5y strictly less than 7. Consider 2x plus 5y equal to 7. When you put x equals 0, you get y equals 7 by 5, which is 1 point something. And when you put y equals 0, you get x equals 7 by 2, which is 3 point something. Fine. So somewhere here is 3, somewhere here is 1. This is 1 point something, 3 point something. And so when you join these two, you actually get the straight line representing 2x plus 5y equal to 7. Because I am not interested in the points which satisfy 2x plus 5y equal to 7, this line will be drawn as a dotted line. Is it clear? This line will be drawn as a dotted line. Now I want all those x comma y for which 2x plus 5y is strictly less than 7. Take up any point which is not lying on this particular line, suppose origin, put x equals 0, y equals 0, 0 plus 0 is less than 7, this is true, and therefore the region represented by this is this. The region represented by the inequality 2x plus 5y strictly less than 7 is this region. This is that region represented by this inequality. Is this a convex set? Yes, of course it's a convex set, because you pick up any 2 points in this region. Anywhere you pick up any 2 points in this region, the line segment joining them is always going to lie in the same region. So this is definitely a convex set. I have to find out which one is not a convex set. This is a convex set. What about this, x square plus y square less than equal to 4? If I talk about x square plus y square less than equal to 4, this is nothing but a circle with center at origin and radius equal to 2. If I talk about x square plus y square equal to 4, it is a circle with radius 2 centered at origin. And x square plus y square less than equal to 4. Equal to 4 is all the points on the boundary of the circle. X square plus y square equal to 4 is actually being satisfied by all the points on the circle. I want all those points x comma y which satisfy x square plus y square is less than 4. For that I will have to pick up a point which is not lying on the boundary, that is origin. So if I plug in x equals 0, y equals 0, I get 0 plus 0 is less than 4, which is true, and therefore the region consisting of the origin is going to be my feasible region. So the region represented by x square plus y square less than equal to 4 is the points inside the circle and the points on the boundary. Is this a convex set? Yes, of course, you pick up any 2 points in this region, the straight line joining them is always going to lie in the same region. So even this is a convex set. I am going to say this is a wrong option because I want to find out which is not a convex set. What is this? All those x such that mod x is equal to 5. All those x such that mod x is equal to 5. Mod x equals 5 means what? I can rewrite this as mod of x minus 0 equals 5. That means distance between x and 0 is 5. Which are the points on the real line whose distance from 0 is equal to 5? Obviously 5's distance from 0 is equal to 5 and minus 5's distance from 0 is equal to 5, right? These are the only 2 points whose distance from 0 is equal to 5. So inside this set only 2 points will lie, 5 and minus 5. All those x such that mod x is equal to 5 is the set consisting of 2 points minus 5 and 5. Can this ever be a convex set? No. The set consisting of discrete points, finitely many discrete individual points, can never be a convex set, because if only these 2 points are there in this region, then the straight line joining them is never ever going to lie in this set, because the straight line joining them is going to consist of infinitely many in-between points which are not there in my set. So it is this particular set which is not a convex set. And this is clearly representing an ellipse. You can write this as 3x square upon 6 plus 2y square upon 6 equal to 1. That would give you x square upon 6 upon 3, that is x square upon 2, that is x square upon root 2 square. 2y square upon 6, which is y square upon 3, that is y square upon root 3 square. So it will be x square upon root 2 square plus y square upon root 3 square equal to 1, and that is going to give you an ellipse with major axis along y axis, x square upon root 2 square plus y square upon root 3 square equal to 1. I want less than equal to 1. If I bring 6 over here, this is 3x square upon 6 plus 2y square upon 6 less than equal to 1. Equal to 1 is satisfied by all the points on the boundary. Less than 1 is obviously satisfied by all the points inside the ellipse. Because when you put x equals 0 and y equals 0, you get 0 plus 0 is less than 1, which is true. So this happens to be my region represented by 3x square plus 2y square less than equal to 6. And this is clearly convex because you pick up any 2 points in this shaded region, boundary is also included. When you join those 2 points, the straight line consisting of those 2 points, joining those 2 points, is lying in the same region. So even this is a convex set, so this is a wrong option. Fine. Moving to the next, we have which of the following statements is correct? Every LPP admits a solution, wrong. An LPP admits unique optimal solution. Wrong. We have witnessed LPPs which have more than one optimal solution. A is wrong, B is wrong. If an LPP consists of two optimal solutions, then it has infinitely many optimal solutions. This is true. If you have two optimal solutions, then all the points on the line segment joining those two optimal solutions are also optimal solutions. So whenever an LPP admits two optimal solutions, all the points on the line segment joining them are also optimal solutions. So there are infinite number of optimal solutions. Clear? And then it is written the set of all feasible solutions is not a convex set, which is false. We have done this as a theorem that the set of all feasible solutions of an LPP is definitely a convex set. In fact, it's a convex polygon. By graphical method, the solution of this linear programming problem would be what? Let's begin. We need to plot all the constraints and also take into consideration this non-negativity restriction. Let's begin the plotting. You all know how to carry out the process. 3x1 plus 2x2 equal to 18 you will be considering. First constraint, when x1 is 0, x2 is 18 upon 2, that is 9. When x1 is 0, x2 is 9. When x1 is 0, x2 is 9. When x2 is 0, x1 is 18 upon 3, that is 6. So this is 6 comma 0. Fine. If you join them, this gives you the equation of the straight line 3x1 plus 2x2 equal to 18. You are interested in 3x1 plus 2x2 less than and equal to. So all these points will definitely come. I need to decode which are the points which satisfy 3x1 plus 2x2 less than 18. For that, put x1 equals 0, x2 equals 0 because 0 comma 0 is not lying on this line. This gives you 0 plus 0 is less than 18, which is true. So everything on this side of this line is going to be my region represented by 3x1 plus 2x2 is less than equal to 18. Then you have x1 less than equal to 4. That means x1 equal to 4 is going to be this line. This is x1 equal to 4. So this point will be 4 comma 0. I want x1 less than equal to 4. So everything on this side. And then you have x2 less than equal to 6. So 6 is going to be somewhere here. This is x2 equal to 6. Less than equal to 6 would be below this line. And x1 greater than equal to 0, x2 greater than equal to 0 is going to make you fall in the first quadrant. So in the first quadrant, on this side of 3x1 plus 2x2 equal to 18, below x2 equal to 6, to the left of x1 equal to 4, the common region comes out to be nothing but this. What are these points? This point is 0 comma 6. I can say this is my feasible region. Firstly, this is my feasible region which is bounded, and therefore I just need to pull out all the corner points, find out the value of z over there and see what is my optimal solution. So let's do that. What is this? This is the intersection of 3x1 plus 2x2 equals 18 and x2 equals 6. If you put x2 equals 6, you get 6 into 2, 12. 18 minus 12 is 6. 6 upon 3 is 2. So x1 is 2, comma 6. And here, what is it that you get? This is the intersection of x1 equals 4 and this line. When you put x1 equals 4, you get 4 into 3, 12. 18 minus 12 is 6. x2 would be 6 upon 2, that is 3. So this point would be 4 comma 3. x1 is 4, x2 in that case is coming out to be 3. So my corner points are 0 comma 6, 2 comma 6, 4 comma 3 and 4 comma 0 of the feasible region. Z is 3x1 plus 5x2. Three into 0 is 0, 5 into 6 is 30, 3 into 2 is 6, 5 into 6 is 30, so this is 36, 4 into 3 is 12, plus 5 into 3 is 15, this is 27, 4 into 3 is 12. You are interested in maximizing, right? Maximum value is 36 being obtained at 2, 6. So the solution is 36 which is being obtained at x1 equals 2 and x2 equals 6. Clear? Next I have the region represented by this inequality or this inequation system is what? Let's see. X and y are given to be non-negative, that means the portion which is being represented by this inequations is the first quadrant. Then I have x plus y greater than equal to 2, x plus y greater than equal to 2. I have drawn this line of x plus y equal to 2. So this point would be obviously 2, 0 and this would be 0, 2. When you put x equals 0, you get y equals 2, y equals 0, you get x equals 2. This is x plus y equal to 2. I want greater than equal to 2. Greater than equal to 2 would be what? If you put x equals 0, y equals 0, you get 0 plus 0 greater than 2, which is false. So the region containing the origin is not going to be the shaded region. This would be the shaded region which is not containing the origin. Fine. Then you have x plus 2y is greater than equal to 3. X plus 2y is equal to 3 is first of all you consider. When you put x equals 0, you get y as 1.5. So somewhere here. And when you put y equals 0, you get x equals 3. When you join them, this is what you have as x plus 2y equal to 3. You want not just equal to 3 but greater than equal to 3. When you put x equals 0, y equals 0, you get 0 plus 0 greater than 3, which is false. So everything on this side of the line which is not containing the origin is my shaded region, and therefore when I talk about the intersection of region represented by this inequation and the first quadrant given by x and y non-negative, I actually get what region? The intersection comes out to be this region. This is what the intersection comes out to be. This is my feasible region. And the nature is that it is unbounded. The nature of this feasible region is that it is unbounded. Understood? So the region represented by this inequation system is an unbounded region. Maximize subject to these constraints. So let's begin maximizing this problem. So you have what? X plus y needs to be maximized. Okay. X minus y less than equal to minus 1. X minus y equal to minus 1 when you consider, when you put x equals 0, y is 1. And when you put y equals 0, x is minus 1. When you join them, you get this, right? This is minus 1 comma 0, this is 0 comma 1. This is x minus y equal to minus 1. I want x minus y less than and equal to minus 1. This is equal to minus 1. What about less than minus 1? If you plug in x equals 0 and y equals 0, you get 0 minus 0, which is 0 is less than minus 1. That is true. So what is going to happen? In here it is x minus y less than equal to minus 1. You have 0 minus 0 is 0. 0 is not less than minus 1. 0 is greater than minus 1. So the region not containing the origin is going to be the shaded region being represented by x minus y less than equal to minus 1. Let's talk about the other inequality. It is minus x plus y less than equal to 0. Minus x plus y equal to 0, first you consider, you get y equals x line. Y equals x line is going to come exactly this way. This is y equals x. I am interested in minus x plus y less than equal to 0. This is minus x plus y equal to 0. What about less than 0? If you put, this is already passing through origin, so I cannot put x equals 0, y equals 0. Just try and put 1 comma 0. Put x equals 1 and y equals 0. Why 1 comma 0? Because 1 comma 0 is not lying on this line. When you put x equals 1 and y equals 0, you get minus 1, and minus 1 is definitely less than 0. So the region which is containing minus 1, containing 1 comma 0 is going to be the region represented by this inequation of minus x plus y less than equal to 0. So all the points on this line and in the portion that I am shading is the region represented by minus x plus y less than equal to 0. And then it says x and y is non-negative. That means I am only asked to consider the shaded portion in the first quadrant. So this, everything here, and I have everything here in the first quadrant. What is the intersection of these two regions? Is there any intersection? Absolutely. In the first quadrant you can see there is no point x comma y which is coming in this region also, coming in this region also, and coming in first quadrant also. There are points coming in this region and first quadrant, all these. There are points coming in this region and first quadrant, all these, but there are no points x comma y satisfying this inequation also, and coming in first quadrant also. So I am clearly going to say there exists no feasible region, and therefore there does not exist any maximum value of z. I cannot maximize z. This is an example of an LPP, or basically that's what, it's an example of an LPP which does not have any optimal solution. Next I have minimize z equals this. I am supposed to minimize now subject to certain constraints. So exact same scheme is going to be followed as we are doing. Same thing you need to do again and again. This is the pattern of LPP problems only. First constraint is x plus 3y greater than equal to 3, x plus 3y equal to 3. When you put x equals 0, y is 1, and when you put y equals 0, x is 3. Okay. This is the straight line representing x plus 3y equal to 3. This is 3 comma 0 and this is 0 comma 1. Clear? Greater than equal to 3. This is equal to 3. For greater than 3, plug in any point which is not lying on this line. Put x equals 0, y equals 0, 0 is greater than 3, this is false. So everything on this side of the line is going to be my region represented by x plus 3y greater than equal to 3. Points on the line and points on this side of the line not containing the origin. Then I have x plus y greater than equal to 2. So plot x plus y equal to 2. This is how it will be plotted. This is 0 comma 2 and this is 2 comma 0. This is x plus y equal to 2. I want greater than equal to 2. So this is equal to 2, greater than 2 would be which side? If you put x equals 0, y equals 0, you get 0 plus 0 is not greater than 2, it is less than 2. So the portion which is lying on the other side of this line, that means not containing the origin, is going to be my feasible region represented by this inequation. And then you have the first quadrant. So the intersection therefore is coming out to be this, of the region represented by this inequation and the first quadrant. This is the intersection. So this is my feasible region, which is clearly unbounded. I am wishing to minimize my function. So I need to identify the corner points. Corner points is this point of my feasible region, this point and this point. What are the coordinates of point B? For that I will have to solve the equations of these two lines. X plus y is 2, so x is 2 minus y. 2 minus y you plug in here, 2 minus y plus 3y equals 3. So you get 2 plus 2y equals 3, y is 1 by 2. If y is 1 by 2, x is 2 minus 1 by 2, which is 4 minus 1, that is 3 by 2. So you get 3 by 2, comma 1 by 2. You have got the corner points with you. Corner points have come out to be 0, comma 2, 3 by 2, comma 1 by 2, and 3, comma 0. Z is what? 3x plus 5y. It is 3x plus 5y. When you put x equals 0 plus 5 into 2, so this comes out to be 10. 3 into 3 by 2, that is 9 by 2, plus 5 by 2, 14 by 2, that is 7. And 3 into 3 is 9, so this is actually my minimum value. But can I declare this to be my optimum value? This is the optimum minimum value of z which is being obtained at 3 by 2, comma 1 by 2. No, not right now. First of all, because this is an unbounded region, the other strategy is going to follow up. Not directly from this table, I will be extracting out this to be the minimum optimal value of z being obtained at this corner point. But first of all, I will be plotting the region represented by 3x plus 5y strictly less than 7, because I am talking about minimum. So if I talk about 3x plus 5y strictly less than 7, region represented by this, you know when x is 0, y is 7 by 5, which is 1 point something somewhere here, and when y is 0, x is 7 by 3, which is 2 point something, that is somewhere here. I am not interested in 3x plus 5y equal to 7. That means points which are going to lie on the line 3x plus 5y equal to 7 are not of my interest. They are not going to lie in this region. So I will be drawing this line as a dotted line. The only thing I need to ensure is whether that line is going to pass through point B or not. So that is going to be ensured if point B satisfies this equation 3x plus 5y equal to 7. If you put x equals 3 by 2 and y equals 1 by 2, you know 3 into 3 by 2 plus 5 into 1 by 2 gives you 14 by 2, which is equal to 7. That means 3x plus 5y equal to 7 is definitely going to pass through point B. So I have this as the line represented by 3x plus 5y equal to 7, which is clearly going to be a dotted line because I am not interested in the points lying on this line. Is it clear? What is the region represented by 3x plus 5y strictly less than 7? When you put x equals 0, y equals 0, you get 0 plus 0 less than 7. That means everything on this side of the line is the region represented by 3x plus 5y strictly less than 7. Fine. So only on this side of the line, not points on the line and not points on the other side of the line are being in this region. This is the region represented by 3x plus 5y strictly less than 7. Now this region has absolutely no point common with the feasible region. The only point common was seen to be point B, which is lying in this region also, in this region also, but actually point B is not lying in this region because point B is lying on the line 3x plus 5y equal to 7, and the points on that line are not included in the region of 3x plus 5y less than 7, and therefore there is absolutely no intersection between this region and the feasible region, and therefore there is no minimum value less than 7. There is no point at which this minimum value is obtained or lesser than 7 is obtained. There is no point in my feasible region in which a value of z lesser than 7 is obtained. 7 is my minimum value. So this is my optimum value and this is my solution. Optimum value of z and this is my optimal solution, 3 by 2 comma 1 by 2. Let's move on to the next question. We have minimize and maximize z equals this subject to these constraints. Let's try to do this. Again, we have to do the same thing. So I have y-axis, x-axis. So here you can see the figures x plus 2y is less than equal to 120, x plus y is greater than equal to 60, x minus 2y is greater than equal to 0. So let's talk about plotting 10, 20, 30, 40, 50, 60, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. This is 60, this is origin. Just for convenience. You have first constraint x plus 2y equal to 120. Let's consider it as an equation. When you put x equals 0, y is 60. And when you put y equals 0, x is 120. Fine. When you join these two, what do you get? So when you join these two, you get this straight line x plus 2y equal to 120. Which region would be less than 120? This side or this side? Put x equals 0, y equals 0, you get 0 plus 0 is less than 120. I want less than 120, so everything on this side of the line along with points on the line is going to be the region represented by x plus 2y less than equal to 120. Then you have x plus y greater than equal to 60, so x plus y equal to 60. When x is 0, y is 60, when y is 0, x is 60. So I have this as the line x plus y equal to 60, greater than equal to 60. Greater than equal to 60, put x equals 0, y equals 0, right? 0 is less than 60, so this side of the line. Okay? For x plus 2y equal to 120, for this line, I am saying that the region containing the origin is going to be the region represented by x plus 2y less than equal to 120, and for x plus y equal to 60 line, the region not containing the origin, that is the other side of the line, is going to represent the region x plus y greater than equal to 60. Thirdly, I have x minus 2y greater than equal to 0. This means x is equal to 2y. If I talk about this as an equation, x equals 0, y equals 0 is going to satisfy, so the line is going to pass through the origin. When you put y equals 30, x is 60. So 60 comma 30, 60 comma 30 somewhere here, this is 60 comma 30 which is going to satisfy the equation of this line, and so the line is going to pass through this. This is my line x minus 2y equal to 0. I want x minus 2y greater than equal to 0. This already line is passing through the origin, so let me consider a point not lying on this line, say 10 comma 0. When you put x equals 10, y equals 0, 10 is greater than 0, that is true, so everything below this line is going to be the region represented by x minus 2y greater than equal to 0. So this side of the line, and below this line, that means this is my feasible region. Okay, this is my feasible region. X is 60, y is 30. X is 60, y is 30. In here, that is what is being represented first of all. So what are my corner points of this feasible region? This feasible region is bounded. Can you see that? This is A, B, C and D. This is my feasible region. Fine. Corner points are what? What is this point? This point is the intersection of this line and this line. X plus y equal to 60 and x is equal to 2y. In place of x put 2y. 2y plus y is 3y. 3y is equals to 60, that means y is 20. And x was 2y, so 2 into 20 is 40. You put x equals 2y, you get 3y equals 60, y is 20. If y is 20, x is 40. B would be what? Intersection of this line and this line. This line is x equals 2y. Put x equals 2y, you get 4y equals 120. 4y equals 120, so y is 30. If y is 30, 30 into 2 is 60. So actually what is going to happen is that this point that we have plotted over here is not going to come over here. It is going to actually be here on this line, 60 comma 30. Fine. So in this way also you can decode the exact region. So I have A, B, I have C, I have D. My corner points are there with me. They are 40, 20, 60, 30, then you have 120, 0 and 60, 0. Z is 5x plus 10y. This gives you what? 5 into 4 is 20. 200 plus 200 gives you 400. Right? 6 5s are 30. 300 plus 300 gives you 600. 120 into 5. Again 600. And this would be 300. So you can clearly see this is max, this is max, and this is min. So minimum clearly is being obtained at just one point. So the optimal solution for minimum value of z is 60, 0 and the minimum value of z is 300. But optimal solutions for maximum value of z, because these two, there are 2 points at which maximum value is being obtained, that is 600 is the maximum value of z which is being obtained at these 2 points. That does not mean that these 2 points are optimal solutions for maximizing z. The entire straight line, all the points lying on the line segment joining these 2 points is my optimal solution for maximizing z. So the entire line segment joining 60, 30 and 120, 0, all the points lying on this segment are optimal solutions for maximizing z. All these. Fine. So what can I say? Minimum value of z is 300, which is obtained at exactly one point. So there is a unique solution for the minimizing z problem. But maximizing z has infinitely many optimal solutions, but its maximum value is 600. So one part has unique solution and one part is coming up with infinitely many solutions. That is the flavor of this problem. Let us look at the next question. Next question is talking about manufacturing. Let us see what it is trying to say, and side by side try to plot it in a table. First of all, a company manufactures 2 types of novelty souvenirs made of plywood, souvenir of type A and souvenir of type B. So type A souvenir and type B souvenir. Type A require 5 minutes for cutting and 10 minutes for assembling. So there are 2 jobs, cutting the souvenir and assembling the souvenir. In minutes we are talking about the time. Unit is very important. So type A requires 5 minutes in cutting and 10 minutes in assembling. Souvenir of type B requires 8 minutes for cutting and 8 minutes for assembling. There are 3 hours 20 minutes available for cutting. So what is the total availability? Availability has to be written in minutes only. Total hours or minutes available for, because we are talking about minutes. Total minutes available for cutting is what? 3 hours 20 minutes. 3 hours means 3 into 60 minutes along with 20 more minutes. These are the number of minutes available for cutting in total. This gives you 200 minutes. And it says 4 hours for assembling. 4 hours for assembling means 4 into 60 minutes, which is 240 minutes. So in total there are 200 minutes which can be given to the job of cutting and 240 minutes in total which can be given to the job of assembling. The profit is rupees 5 for each for type A and rupees 6 each for type B souvenir. So how many souvenirs of each type should the company manufacture in order to maximize the profit? Okay, so let us begin. We know how to deal with such problems. I am saying let X be the number of souvenirs of type A and Y be the number of souvenirs of type B. I need to find out how many types of souvenir A and how many souvenir B should I actually manufacture to maximize my profit such that all these constraints are satisfied. So, suppose X is the number of type A souvenirs to be manufactured and Y is the number of type B souvenirs to be manufactured. Then, if one souvenir of type A is requiring 5 minutes in cutting and one souvenir of type B is requiring 8 minutes in cutting, that means X souvenirs of type A will be requiring 5x minutes in cutting and Y souvenirs of type B will be requiring 8y units in cutting. That means if I am manufacturing X souvenirs of type A and Y souvenirs of type B, in total I am requiring 5x plus 8y minutes in cutting them. But in total, these number of minutes which are spent in cutting type A and type B X and Y souvenirs, they should not exceed 200 minutes. So, this should be less than equal to 200. This is my first constraint. Second constraint, a souvenir of type A requires 10 minutes in assembling. So, if I am manufacturing X souvenir A, souvenirs of type A, then 10 into X is the minutes spent in assembling them, and similarly 8 into Y is the minutes spent in assembling the Y type B souvenir. So, in total if I am manufacturing X of type A and Y souvenirs of type B, I am investing 10x plus 8y minutes in assembling them, but in total I can only invest 240 minutes. So, this assembling time should not exceed 240. This is my next constraint. This I can also write as 5x plus 4y is less than equal to 120. Moreover, the number of souvenirs can never be negative. So, I have x greater than equal to 0, y greater than equal to 0, and what is my objective function is to maximize the profit. On one souvenir of type A, the company, this manufacturer is earning 5 rupees profit. So, if he is going to manufacture X souvenirs of type A, he will be earning 5x rupees profit. On one souvenir of type B, the manufacturer is earning 6 rupees profit. So, on Y souvenirs of type B, he will be earning 6y as profit. So, in total this is his profit. Let us say this is my profit function and I need to maximize this profit function. So, what is my actual problem? Therefore, mathematical formulation of the problem is very simple. Maximize z equals 5x plus 6y subject to 5x plus 8y less than equal to 200, 5x plus 4y less than equal to 120, x non-negative, y non-negative. The moment you have with you the very mathematical formulation of this problem, you don't require anything. You just need to graphically plot the solution and you will be done. So, let us begin. Okay. First is 5x plus 8y less than equal to 200. When x is 0, y is 200 upon 8. What is that? This gives you 25, right? When x is 0, y is 25. So, say this is somewhere 25, and when y is 0, x is 200 upon 5, that is 40. This is 10, 20, 30, say this is 40. And this is 0, 25, because you can see 200 upon 8, yeah, 25. And therefore, when you join these two, this is the equation of the line 5x plus 8y equals 200. Then you have 5x plus 4y less than equal to 120. First of all, let us decode the region represented by the in equation 5x plus 8y is less than equal to 200. If you put x equals 0, y equals 0, 0 plus 0 is less than 200. So, this side of the line would be the region. Then I have 5x plus 4y less than equal to 120. When x is 0, y is 30, and when y is 0, x is what? 5 into 2 is 10 and 5 into 4 is 20. So 24 somewhere here, because you all know what is 24 into 5, 120. So you get 24 comma 0. This gives you what? This as the line represented by 5x plus 4y equal to 120. If you put x equals 0, y equals 0, 0 plus 0 is less than 120, yes, it is true. So this side of the line, and already this means the first quadrant, so my feasible region is going to be this. This is my feasible region with these 4 as corner points. What is this point? The intersection of these two lines. 5x plus 4y is equal to 120. So 5x is 120 minus 4y. Put it over here. 120 minus 4y plus 8y, this is plus 4y, equals 200. 200 minus 120 is 80. 80 upon 4 is 20. So y is going to be 20. If y is 20, 20 into 4 is 80. 120 minus 80 is 40. 40 upon 5 is 8. Isn't it? If y is 20, 20 into 4 is 80. 120 minus 80 is 40 and 5 into 8 is 40, so x is 8. These are my corner points. The moment I am through with the corner points, now I am not far away with finding out the maximum profit. Corner points are 0, 25, 8, 20, then 24, 0, and obviously 0, 0 is not going to give me anything, but okay, that's a corner point. And z was coming out to be 5x plus 6y as my profit function. 5 rupees for each souvenir of type A and 6 for each souvenir of type B. So 6 into 25 would be what? 150. 150 rupees profit if you manufacture no souvenir of type A and 25 souvenirs of type B. If you manufacture 8 souvenirs of type A, 5 into 8 is 40 plus this is 120, this is 160, 20 into 6 is 120, 8 into 5 is 40. Then if you manufacture 8 souvenirs of type A and 20 souvenirs of type B, you will be earning 160 rupees profit. What is 24 into 5? We already calculated. It's 120. If you manufacture 24 souvenirs of type A and no souvenir of type B, 120 rupees profit, and here 0 rupees profit. So obviously this is my max. Max profit is 160 rupees, which is earned when you manufacture 8 souvenirs of type A and 20 souvenirs of type B. That is my optimal solution. Is it clear? So you can write this as your feasible region. Maximum profit earned is 160 rupees, and that you can earn when you manufacture 8 souvenirs of type A and 20 souvenirs of type B. That finishes my discussion over the 10 questions. That's it from my side. Revise them nicely. Thank you.